lecture from Igor Klebanov. So Igor is not just a lecturer, but also one of the scientific organizers for this school. So we're all very grateful to him for putting all of this program together for you. He's going to talk about large N models.
Yeah, thank you very much, Oliver, and I'm very grateful to all the organizers from here in Boulder, because they're doing definitely the bulk of the work. And Tom,
you did the boundary.
I set the boundary condition. Yeah, Tom, Oliver, Emily have been absolutely great, and I'm happy to be in Boulder. Actually, coming to TASI, I can't help reminiscing a bit. I was a student in TASI in 1985 before it was in Boulder. Actually, there was a period of 5 years when it started, I think, in '84 at the University of Michigan, and then for 5 years it moved every year to a new place. So '85 was at Yale. Then I don't remember precise sequence. I think it was at Brown in '87 or '88. And then people realized that it has to be automatized somehow, because to do it from scratch every year is incredibly hard. And also some of these destinations were less popular than others. And then, or some were more popular than others. And then since 1989, it's been here in Boulder. And actually, the first time I lectured was in TASI 1989, when Tom was the scientific director, and it was called From Actions to Answers. I won't tell you what I lectured about. It was, in retrospect, it's not very important, but it was.
I have a copy of the proceedings.
Yeah, whatever. It was about wormholes and how the cosmological constant is exactly 0, but since then we found out. But then definitely the highlight of my TASI career was back in 1999, which I think was the second.
Which was the year that I was.
Exactly, I was going to mention that. This was an extremely exciting school where many lectures, so the ADS, TFT, kind of materialized mainly in 97, 98, and then 99 there were many series of lectures about that. It was extremely exciting, and many of the students, I'm happy to see, are now professors in various nice places.
At least a dozen, I count.
Yeah, it was, and Oliver, I remember you very well. Also, another person I remember well is Lubos Schmatl. No, he knew a tremendous amount. I mean, it was clear. He apparently solved all the problems in Polchinski's string book, and it was extremely exciting. And so I looked back at my TASI lecture. So Johanna's lectures inspired me to remember this D3 brain perspective. So I'm not really going to talk about it, but if you want to read about like the thinking in those days, it's maybe a bit outdated in some ways, but and you'll hear more from her. But so one thing about this stacking brain perspective is that you stack a large number of these 3 brains, and then it creates this curved metric. But you have to remember that this 3-brain metric has an extra 1. It's not exactly an ADS-TFT. What you get as R goes to 0, then you get ADS 5 crosses 5 in Poincare coordinates. But the 1 makes it kind of open up at large R into flat 10-dimensional space. And that was the perspective that some of us used in those days. So you can send like a wave packet from the asymptotically flat space, and it kind of tunnels into ADS space. So it gives you, so if you want to read about that perspective, you can read it there. And so the power of large N, so in retrospect, one thing that large N gave us is almost 20 years of ADS-CFT in a sense, because most tests of ADS-CFT really very much rely on large N. So we know little beyond the large N limit. So as you heard, for example, in ADS-CFT, there are two important things. One is this sort of 't large N limit, 't large N, where you send G and mills to 0, and you send n to infinity, and you keep lambda, which is gn mil squared, n fixed. Okay, but so the generic thing is precisely this. Lambda does not have to be large. Okay, and this doesn't rely on any details of the theory. This type of large n limit, in some sense, exists in a huge variety of theories, right? For example, QCD, etc. So, so certainly what we know relies on this limit, but then we have this sort of, I would say, so this is generic 12th large n, and then there is what I would call rare event. Rare event is the possibility to take lambda to infinity and obtain weakly curved dual. Obtain lambda to the 4 being much, much greater than alpha prime squared. By the way, so some of what I'm going to say is like a little bit like the reverse of what Daniel Harlow just told us, because he wanted to start from ADS and sort of go to CFT, and I want to start more from the CFT perspective or just field theory perspective and see which parts of it give us ADS. But I think the applicability of large n limit is kind of more general than just ADS. I mean, ADS is one of the great things about it, but then there are various other nice properties. So I want to therefore separate a bit this sort of generic large n story from some special features that appear to happen in some particularly beautiful symmetric theories, which have extra symmetries like supersymmetry. So let me talk about. So I'll kind of go a little bit back and forth between these two, but I want to discuss. So what are I think 3 generic classes of large n limits that we use? So certainly 12th limit you heard a lot about, but it wasn't historically the first one. So historically the first one was were these various ON magnet models. And these are examples of so these are what you would call the vector large n behavior. Large n. So in these theories, for example, the most basic theories where you try to generalize Heisenberg magnet, which has O3 symmetry, to you want to find some kind of computational tool to develop some approximation scheme for the second order phase transition in the Heisenberg magnet. And this is exactly that type of story. So in this vector large n limit, let me call C some generalized central charge number of degrees of freedom. So here C scales as n. Okay, so basically the degrees of freedom are like n vectors of some ON symmetry group. Okay, and this limit was, I think it was invented partly by Stanley, who is a famous expert on statistical mechanics. And basically you're often faced with some kind of strongly coupled system where there is no obvious expansion parameter. And then, and if you get desperate, you invent this artificial expansion parameter, which is 1 over n. So for example, if you want to describe the O3 model, you start imagining what if 1/3 is really a small parameter. So you formally generalize from O3 to ON, and then try to develop a series of 1 over n corrections. Okay? So just to make it more concrete, well, I'll say in a bit more detail how these models work. They're definitely probably still have the most physical application, or at least they're probably the most generic. They appear in all sorts of situations, and the nice thing about them is that the large n limit is solvable and can be studied analytically. So it's really an example of solvable large n behavior. 1 over n expansion. For example, if you want to go to some fixed point and develop the dimension of some operator in powers of 1 over n, it can be done. Moreover, it has been done to some pretty high order. Okay, so this I think originated in the 60s or even earlier. Okay, then so it's a very beautiful and nice example of theoretical physics. Then there is the 't Hooft limit, which I think 't Hooft limit. You saw examples of it in the sun-equal force superring-mills, but 't Hooft didn't think about n-equal force superring-mills. He was just thinking about QCD, or generic non-abelian gauge theory. So one reason it's so popular is that it applies to, for example, SUN gauge theory. Where the gauge fields themselves are in the joint representation. Joint. In other words, you just have a mu, one upper and one lower index, and this you can call the matrix large n limit. So you can call this the matrix. And here there is some good news and there is some bad news. So the good news is that so it's in general reduces to planar diagrams, and this is what Johanna already showed us. So there is reduction to planar Feynman graphs, but not solvable in general. It's only solvable if there is some specific other simplification, not solvable in general. I will review a tiny bit the models that are explicitly solvable. They usually involve models of matrix degrees of freedom in very low dimensions, like in 0 dimension or in 1 dimension, something like this. Okay, so this is, in some sense, all has been known for a long time, and certainly this ADS-CFT very much relies on this matrix large n limit, but it also one of the amazing secrets of this, n-equal force superring-mills or D3 brane bulk duality is the possibility to dial. You have this flat direction, which of the coupling constant, which you can interpolate between two different solvable limits, right? So for lambda much smaller than 1, can use Feynman usual QFT techniques, namely planar Feynman diagrams, for example. But for lambda much bigger than 1, just use supergravity. I think this really was the sort of the revolutionary thing, like in the thinking, when we were working on this stuff back in 97, 98. This was really a completely unusual thing, because certainly people knew about the matrix large end limit and so on, and people knew about the simplification. So one possible thing that you can study, for example, so you've already seen what type of fields there are in n=4 super Young mills, and there is one special operator called Kanishi operator, right? So Kanishi. So suppose you want to study the dimension of some single trace operator. Yeah, Daniel told us about the separation at large n between single and multi-trace. So there are these six adjoint massless fields phi I, and just about the simplest operator you can write down would be something like O Kanishi, which is sum from 1 to 6 trace phi I squared. It turns out that this is not one of these protected operators. So one special thing about n=4 super Young mills is that there is a whole bunch of operators which are dual to Kaluza-Klein state, which are actually symmetric traceless polynomials in phi I. So, for example, so this is not protected. Not protected by supersymmetry. You've already heard about some things that are protected, right? So the simplest class that are protected would be things like trace phi I1, phi I2, dot phi IK, and you have to completely symmetrize these indices and make them traceless. So these are symmetric traceless polynomials. So symmetric traceless polynomials, symmetric traceless. Do you know what they're dual to in the ADS space? Probably some of you know. Which states are they dual to? Right. Kaluza-Klein mode. So if you just look at some particular excitations, yeah, luckily for ADS-CFT, some people did really hard work years before ADS-CFT was formulated. And in particular, Kim Romans and Van Nieuwenhuizen computed the complete spectrum of ADS 5 process 5. And there were some particular mixtures of graviton and graviton and dilaton excitation. No, not dilaton, but so there were modes that have masses that corresponded to exactly these. So if you look at their dimensions, so their delta would be just k, because phi has dimension 1, right? So it would be k. Then you compute the one loop correction, you get 0. You compute two loop, you get 0. So it's exact. So you can extrapolate from lambda being much smaller than 1 to lambda much bigger than 1 and compare boldly. And so it's a test of ADS-CFT, but it's a somewhat boring test, right? It's sort of a test on the level of just matching the number of states. So this is exact, right? So this we already knew pretty well already in 98 that these tests are passed. But there have been, so what have people been doing in these 19 years? Well, they worked very hard. And actually one of the tests was for this operator. So does anyone know what is the dual state to this? What is the dual state in ADS-CFT that dual to this. Whenever you see something like this, which is not protected, the candidate would be a massive string. Okay, and it turns out, since this is the so if you look at the spectrum of massive string states, then so the spectrum of massive string states would be so massive closed string states, massive closed strings, and they have all masses of order 1 over alpha prime. So in fact, their masses would be m squared is 4n divided by alpha prime, right? And n can be 1, 2, up to infinity. And so since this is such a simple state, it's plausible to assume that that when you extrapolate it to strong coupling, it just the description of it would be, here you have this idea space, and you drop to the center just the massive state, just the massive closed string that gets dropped and sits at the center. And we know that this, by the ADS-CFT dictionary, delta is equal to square root of 4 plus ml squared plus 2, right? But here, because this is just 4n over alpha prime, and this is lambda is big, and L to the 4 is like this, so you basically see that this ML is just going to dominate. So this, in the limit lambda much bigger than 1, should start looking like 2 square root of n times lambda to the 1/4. Right? Plus some subleading correction. Okay, so this is a pretty dramatic prediction that essentially all the states, all the operators which are not protected by this amazing symmetry of the theory, their dimensions are going to diverge when you crank up the coupling. And it's a testable prediction. So I think a lot of the work in these 19 years have focused on really checking, is this true or not? And so in the paper with Gopser and Polyakov, we actually conjectured this, but it was a plausible conjecture, but it seemed like would be unbelievably hard to test. So I want to just, your question? Yeah, so I just want to, so the test came from the idea that people noticed that just perturbative expansion. So if you look at this dimension of the Kanishi operator, oh sorry, there are two K's here. Let me call this L. So this is the prediction for large lambda behavior. Now, if you look at the dimension of the Kanishi, of this Kanishi operator, people started computing it perturbatively, and the first few calculations were done just using graphs. So usually people introduce this new parameter, g, which is square root lambda divided by 4 pi, just to remove some extra junky 4 pi. And you get the following few terms. So from one loop term, you explicitly find 12g squared minus 48 g to the 4. That's 2 loop. Then 336 g to the 6. That's 3 loop. Then starting 4 loop, you start seeing zetas coming in. So there is minus 2496 plus 576 zeta 3 minus 1440 zeta 5. And then the really powerful techniques were invented to continue this perturbation theory. And I think the particular breakthrough came from the paper by Gromov, Kazakov, and Vieira. And these papers are really difficult to understand, but the results speak for themselves. So they basically notice some properties of spin chains that are used to develop this perturbation theory. And by now, I think people know to 10 loops or even beyond. Like there are simple monumental accomplishments that would be totally impossible to reproduce directly. So this would be including 10 loops. So you basically know how this function begins. And now what about on the dual side? Well, on the dual side, people weren't resting either. And in fact, it was possible to, so by a series of tricks, they obtained the following terms here. So if you, for example, just look at the Konishi, then you can set this to 1. So one dream was to continue this and to check this 2 lambda to the 1/4 behavior. But then people actually deduce the following terms: plus 2 over lambda to the 1/4 plus 1/2 minus 3 zeta 3 over lambda to the 3/4 plus, it's still a known coefficient, over lambda to the 5/4. And I think so far that's all that's known. And so the question is, if this is really one theory, is there a smooth function that extrapolates between the two? And by now there is, from very precise calculations involving these integrability solution that these people invented, there is now a very precise plot, at least, which some of these plots appeared last year, but they see like so this is built in analytically, and they see matching with these results to very, very high precision. So this one is 2 is like to, I think, ridiculously high precision, but even these terms come out very precisely. So there was a paper I noticed. So one interesting paper was by Hagedusha and Concher, who is a numerical solution. And this is, I can give the HapTH number, it's 1604.02346. Yeah, I'll post all of this anyway on the. But you basically see this rather modest looking curve. Still people have not fully cracked the problem of analytic large N expansion, but this curve very clearly behaves like g to the 1/2 or lambda to the 1/4, and all of these coefficients match. So I think this is sort of one of the truly smoking guns that makes us believe so much that the theory can be continued from weak coupling, defined through the usual Feynman graph techniques, and then once you approach lambda, not that high even, lambda of order 10 or something, it becomes really described by string theory in ADS5, process 5 background. Yeah, question? Well, you can, I think they just solve numerically for the dimension of k, and then they match, they determine these coefficients and then compare with the analytically known coefficients. But I should say that this is a particularly difficult example for them. There was another example which was much simpler, which was called the Beiser-Tiden-Staudacher equation. There, you could actually solve the equation of strong coupling and analytically match a similar story. But yeah, question.
So
No, they are asymptotic series. Yeah, this is certainly, if you look at the behavior of this series, you see that the coefficients do start pretty rapidly blowing up. So, for example, where was this? Yeah, this was, so this is 2 here. This is about minus 3.1 over lambda to the 3/4. And this is already plus 15.5 over lambda to the 5/4. So these are certainly asymptotic series. But this doesn't prevent the matching at large lambda, right? So, yeah. Yeah, this series is not, this series is convergent, this one. Yeah, because it's planar. It's a planar perturbation series. Yes, yes. Yeah, what makes it convergent is the fact that planar perturbation theory is much nicer than the whole perturbation theory. This is one of the examples of the power of large n. So one thing that should be made clear is that all of this depends on the leading large n approximation. So if, for example, so this delta k, of course, has a correction, some other function of g, like let's call it f1 of g over n squared, and so on. And this is a whole separate function which I think people know a lot less about, or it hasn't been computed. So this, it was clear from the beginning that this matrix large n limit, by cutting down to planar graphs, it makes the series convergent within some radius of the 't coupling. So while generic perturbation theory certainly diverges even for small g, this is not the case for this. And this is part of the reason that you can basically start with this convergent expansion and hope to analytically continue it to large g. So it should be a well-defined mathematical problem. And by now people have made good progress on it in some particular cases. Well, you have to pick observables judiciously. I think they have determined some other operators in a similar way. So the beautiful thing is, so delta k, this Kanishi dimension, is like one of the simplest one, and it corresponds to the sort of n equal 1, the lightest string state. You can look for the operator which is the next lightest. Usually the lightest one is the cleanest because it doesn't mix, can't even mix with anything, and so on. But I think there is, I haven't kept track of that literature so much, but they do have successes for other operators. The one, if you want to know when the biggest, in some sense, the cleanest and the biggest success is for the so-called cusp anomalous dimension, which is basically the following quantity, that if you look for an operator of high spin, so if you look at high spin operators, which are like trace phi I, and then you put in covariant derivative, say in the plus direction, phi I, then we know that the delta will be, at weak coupling, will be s plus 2 plus some order lambda correction. So it's another operator which is not protected. And then more generally, for large S, so for large S, you get delta is S plus some function of lambda times log S plus some order S to the 0 term. And this function of lambda is, people call it the cusp anomaly. It's related to Wilson loops with cusps in some peculiar way, but so people call it cusp anomaly function. And this one, the dual state in ADS space turns out to be a long spinning string. So if you look at ADS, global ADS like this, you can have a folded string like this, which is spinning around. And this gives a, basically, you can see this log S divergence, and you can see, so this tells you that for lambda much, much bigger than 1, you find that f of lambda is root lambda over pi minus 3 log 2 over pi plus some order 1 over root lambda. And here, the story is in a way even more successful because there is an equation called the BS equation, which can be solved for any coupling, but you can analytically develop its strong coupling expansion and match to any desired order so this is a kind of stringy calculation where you have like a long spinning string, then you can compute the kind of quantum correction to its energy. Then already this term is more complicated, but it all matches very beautifully. So there is again some kind of weak coupling expansion for f of lambda, and it matches the stringy calculation. So there are a few examples like this. There is no general proof, but these are certainly quantities that are not protected by any obvious symmetry. So I mean, the early tests of ADS-CFT, like around 98, were kind of, people were saying, oh, but how do you know that there aren't two separate theories? One is a theory defined by perturbative expansion and super-Young Mills, and then the other one is this weird string theory in ADS 5 process 5. So in fact, there were some skeptics who wrote papers that, what if there are two functions delta, right? One of them is one function and the other one is another function. They never meet. But I think after 19 years, we basically know that there is only one function and there is only one theory. But I think this particular, so this relies on many kind of confluence of many big ideas. I think the biggest one is still the large N because this whole integrability story is pretty much for the planar theory. Like it is, I think, not known how to extend it beyond the planar limit. So this is the zeroth order thing. And then the other one is this flat direction that allows you to kind of go from one perturbation theory to another perturbation theory. And what's in between is really complicated. But we don't have a full description of what's in between, except in some cases. Okay, so this is at least. In fact, there was an interesting story because the integrists, there was a period of a couple of years when they all were saying that ADS-CFT is wrong because their ansatz for the calculations wasn't general enough, and they were not matching something at for loop. And then suddenly they realized what was missing. They obtained the matching at for loop with the explicit calculation and integrability, and then from then on they went from for loop to infinite loop pretty fast. But okay, so this is one example of power of large N in this particular context. But one thing that I really want to talk about in this series of lectures, so I'm giving this lecture today, which is a kind of a bit of a preview, and then two more lectures next week. And one thing that I'm pretty excited about now is the following fact, that if you asked people, say, a few months ago, what are the two generic sort of large N limits which don't rely on supersymmetry and just rely on counting indices, they would answer two. Like, basically, one would be the vector limit, and the other one would be the 't Hooft limit. Pretty much anyone with few exceptions would say two. But now here comes the third one. Okay, the third one is the so-called, so limit number 3 So large n, third large n limit. Large n limit is the tensor limit. Rank R tensor with R greater than or equal to 3. Now this is, and in this case, obviously C. So in the case of this matrix large n limit, obviously the number of degrees of freedom is going to scale like C is n squared, and here C is going to scale as n to the r, right? Okay, so I, like many people, were sort of misled by the following very simple idea. It was sort of this one-to-many kind of idea that since the vector limit is very easy, and then the complexity jumps as you go from vectors to matrices, and this obviously becomes very complicated and barely tractable, and some mind-bogglingly complicated papers were written just to understand the extrapolation of some operator dimensions. Then what would you say? That once you go on to tensors, then you have a truly unintelligible mess. But amazingly enough, some people already knew that it wasn't the case. And in fact, it becomes simple again. It becomes much simple. It becomes maybe not quite as simple as this vector limit, but vastly simpler than the planar limit. And it turns out that it simplifies again. And this was discovered by a group of people in France, Razvan Gourau, Rivasol, and many collaborators. And recently this was connected with the so-called SYK, Sajdevier-Kitaev models, but I probably will not talk about this aspect. I just want to explain why this limit is so simple. That's a really huge surprise, and that the simplification occurs due to a specifically picked structure of the interaction. Okay, so you have to. The secret is you have to pick the interactions wisely. So you have to pick the interactions carefully. While for vectors and tensors you don't really need to do this, there is more or less a unique way to do it. But in this tensor case, you have to kind of keep your wits about it. And I wanted to explain how this story works. So this tale of three large n limits. Oh, just one disclaimer. So some of you may have heard about other large n limits, right? For example, one in the discussion during Daniel's talk, there was the so-called M-theory limit that came up. It doesn't mean that these three limits are the only ones known. So, for example, there are additional So there may be additional nice simplifications that can occur. So, for example, in one example is the so-called M2 brain theory. M2 brain, or ABJM, Aroni, Bergman, Jeffers, Maldacena theory. So this is widely regarded as a kind of closest relative to n equal 4 super-n mills, but in one less dimension. So this is a particular example in 2+1 dimensions, and it's basically UN level k cross UN level minus k theory coupled to matter, coupled to massless matter. And what does this level mean? It means that there is a so-called Chern-Simons interaction. This Chern-Simons interaction says that you have a term like k over 4 pi and integral d3x a wedge dA. So this is the field corresponding to this gauge group, and then say minus a tilde wedge dA tilde. So in this theory, the analog of 't Hooft coupling, so analog of 't Hooft coupling, it exists. And it would be lambda equal to n over k. So the standard Hooft limit is, so the standard Hooft limit would be standard, in other words, limit number 2, large n limit number 2 is send n to infinity and k to infinity, keeping lambda fixed. But the whole ADS-CFT duality for this theory suggests the existence of a different limit, where you keep k fixed and send m to infinity. And this people often call M-theory limit. So this is a different story. What here is. So what happens is there is, so you could call it exotic, or so what does ADS-CFT conjecture for this theory? It says that the dual is 11-dimensional M theory, which is supergravity, soup-top supergravity, on the background ADS4 cross S7 mod ZK. So obviously, if you want to keep this background the same, you want to keep k fixed. So this suggests the existence of what I could call exotic M-theory limit, where you just say k is fixed and n is sent to infinity. And amazingly enough, there is strong evidence just from field theory that this limit makes sense. And in this limit, the c, the number of degrees of freedom, goes like n to the 3/2. And there is something called f, which is the, you can compute the partition function on the 3-dimensional sphere for this theory. So f equal minus log z on the 3-dimensional sphere is exactly solvable. Well, it's reducible to some special finite dimensional integral, and you can really see that f goes like n to the 3/2 plus all sorts of computable corrections. So in this, So this doesn't fall in this sort of generic classification. And actually, one of the things that I wonder about is this, somehow the existence of these exotic special limits is very much the existence of these large gap theories that Daniel was talking about. The question is, do these theories ever exist in the absence of special symmetries like high degree of supersymmetry? And at the moment, nobody knows, but certainly in the cases where we do know these special limits exist, then they appear only in non-supersymmetric theories. So I would say say that there are two exotic sort of special behaviors where this large gap opens up. One is, so you open up the gap in dimension, open up gap in dimension spectrum, operator dimension spectrum. I think there was a discussion in the previous talk, and I believe people think that this gap is of order n to the 1/3, because that corresponds actually to the Planck scale. I think to some extent this has been established, but obviously this limit is necessary for finding not just ADS dual, but a very weakly curved ADS dual. So the question is, do you always need this sort of extra something to not just have ADS CFT, but have a weakly curved ADS dual? And that's sort of the ultimate dream. We don't have that many examples of this, but that's basically what I wanted to say, that there are, in addition to these three generic limits, there are sort of possible additional special limits, and we want to expand the class of these special exotic limits. Are there any questions? Okay, so having said that, I want to now focus on these more generic theories. And another comment I wanted to make is that when I talk about these generic theories, unlike Daniel, I include theories that actually do have non-singlet operators. So listening to the talks today, you could just think that there are only two types of operators, which are single trace and multi-trace. But for example, in this model, there are neither, right? There are just operators. For example, if you look at the spin operator in the Heisenberg model, it's neither single trace nor double trace. It's just an operator in the vector representation. So these models, they include the non-singlet operators. And I'll say a little bit more. And for them, there is still, like, the large n is powerful. For example, if you look at the field theory, if you look at the field theory description of these ON models, it's something that you can read about in Peskin and Schroeder, right? All of you have read Peskin and Schroeder, right? It's in chapter 13, where there is a discussion of critical phenomena. For example, if you look at the following theory, so suppose our goal is to study these sort of ON magnets. So you make some kind of a lattice. I'll just, for simplicity, make it two-dimensional, although the most interesting case is when the lattice is three-dimensional. And at each lattice, you just have a classical spin pointing in some direction. And this classical spin, so you just have some energy function, which is minus j times sum over nearest neighbors of ni dot nj, right? And n is a n-dimensional vector, right? N is a vector which is acted on by this n. And this, let's say it's a unit vector, so n squared is equal to 1. So for n equals 3, this is just the Heisenberg model, which is very common in nature because molecules can have spin, and there can be these ferromagnetic. So it's ferromagnetic when J is bigger than 0. So then you can look at the partition function Z, which is sum over all spin configurations, e to the minus beta e, and you find the second order phase transition. Find the second order phase transition. And amazingly enough, this second order phase transition is described by essentially 5-4 theory, by ON symmetric 5-4 theory. And this really is in Peskin and Schroeder. So that you just so you take a continuum field theory, which is valid near the second order phase transition. Continuum Q of t looks as follows. You just take the Euclidean action to be integral, say, d dx. Let's just, for definiteness, say it's three-dimensional, d3x. 1/2 gradient phi squared plus lambda over 4 phi I squared. And then you can add a mass term, like m squared over 2 phi I. So the phase transition corresponds to the transition between two phases, which is, so for m squared bigger than 0, you have symmetry unbroken phase, right? And for m squared less than 0, you have Nambu-Goldstone phase. So this phase transition, so phase transition separates the m squared bigger than 0 and m squared less than 0 phases. And this one is the symmetry broken phase. And this is really has applications to nature. For example, the simplest case is when n is just equal to 1. Do you know what this is called? What is? Yeah, this is just the Ising model. So when n is 1, you just take the regular 5-4 theory, and then there is a breaking of Z2 symmetry, right? And the phase transition is just the 5-4 theory in 3 dimensions. So in this theory, we can certainly compute dimensions of operators. So the power of large n for this model is that, for example, you can take, so what are the simplest operators? This operator phi I is just like an average spin operator. You take these spins and average over some largest domain. So phi I is the spin operator. And phi squared is the operator that basically, here it's the mass operator, but people call it the energy operator. So these are the two simplest ones. So this one deserves to be called a single trace operator, right? This one is a singlet. This is phi I. So you can call this a single trace. But this one is just a non-singlet operator in the vector representation. And you can develop the large n expansion for either one. You actually find that for this one, the leading term is exactly the free dimension, 1/2. And then there are some corrections, like eta 1 over n plus eta 2 over n squared, and so on. So, and then similarly for phi squared, in this case the expansion looks like, in this case it's 2 plus some, let's call it eta 1 tilde over n plus eta 2 tilde over n squared. So these are maybe the most useful for physical applications because they describe actual real phase transitions, and these numbers are exactly solvable. They're perfectly well computable. I'll explain briefly how they're computed, but for that we first have to understand why this theory simplifies so much. So strictly speaking, this theory by itself does not have any simple dual ADS description because it's not gauged. So even though gauging maybe in some deep sense is not, but for this model you know exactly what it means to gauge it. You can actually, Yin invented this. You can couple this ON model to an ON Chern-Simons gauge field, and that completely removes this operator from the spectrum, but keeps this operator and certain other ones. And that model is basically what Polyakov and I conjectured to what is dual ADS description, but it does not have a large gap. It's one of these higher spin ADS CFT duals. But even if you don't gauge anything and you have these non-singlet operators, large N is still a very useful and powerful thing. And you can, and one of the points of comparison for this is the recent bootstrap results. So while Monte Carlo calculations don't go usually to very high N, the bootstrap actually is no problem to continue to large N, and they obtained excellent matching with these 1 over N calculations. I should also mention that probably Silvio Pufu will talk about this. Yes.
Just to clarify, the lambda is true.
No, lambda is dimension full. So if you go to for example, if you're working directly in 3 dimensions, right, lambda has dimensions of mass. So in some sense, you can say that lambda flows to infinity. Right, it's just a relevant operator. The picture of RG flow is like this. When you can tune this relevant operator to 0, then you just have a free CFT. Right, so the picture of RG flows is like this. This is actually, it's something that was known long ago, but for some strange reason, many people forgot it, and now it sort of came back, and partly because of bootstrap, or partly for lack of anything better to do. I didn't mean to say that. But it's something that was known, and definitely to Ken Wilson. I mean, it's called Wilson-Fisher approach. Yeah, so the picture is like this. So you have the free UV CFT, that just has lambda equals 0, and it just has free field, right? Then you turn on this relevant perturbation. The important thing is to fine-tune the mass squared to 0, right? So there is one operator that needs to be fine-tuned, which is but once you've done that, so generically you'll just flow to a massive phase. But if you fine-tune the flow, you get this interacting, you can call this Wilson-Fisher CFT. Wilson-Fisher CFT. And this is in some sense, as your question, it should be very strongly coupled, because lambda, in some sense here you have lambda equal infinity. And that's where the large N approach is useful, or could be useful, because you could just develop large N expansion at the CFT. So these things that I wrote here are exactly for this interacting large N CFT. at the free CFT, this delta phi is exactly 1/2, and delta phi squared is 1. So at free CFT, what you have is a delta phi I just 1/2, and delta phi squared is 1. So you see that the fact that this goes from 1 to 2 is a sign of strong coupling. But somewhat mysteriously, most other dimensions don't flow very far. So naively, you would say that these theories should be somehow far from each other. But the actual number, for example, if you look at the numbers for these, for example, for here, you find that delta phi for the 3D easing is about 0.518. And this is amazingly close to 0.5. So a lot of dimensions don't change under this flow. And so you could sort of, if you're an optimist, you could say that large n explains qualitatively why a lot of dimensions don't change. Even though quantitatively it's maybe not so great for small n. But so if you're a large fan of large n, you would say that in this 0th approximation, it should still be 1/2. And the exact number is very, very close to 1/2. So large n is good for these models, if not quantitatively. It's good qualitatively. It becomes quantitatively excellent for n starting around 7 or 8. And I'll show this plot. Okay. Any more questions? So let me just talk then about. So when you look at this theory, you could just say, well, this theory is just a particular variant of 5-4 theory, right? You simply take n fields and construct interactions for these fields in a specific sort of ON invariant way. For vector interactions, this is the only thing you can write down, right? And it's a so-called double trace, right? Because it's a square of a single trace operator. So the only thing you can write down for vector is this double trace. So this is double trace. And now you can keep playing this game for matrices and for tensors. And for there you basically have more freedom. And I want to explain basically how you can use this freedom to help construct a whole new large n limit. Yes? Yeah, I think this does not. That leads to a free theory, I believe. Yes. Yeah, I think for finite time the beta function is positive. Yeah. But if you do it in 3 minus epsilon dimension, then you do get an IR fixed point. But yeah, so strictly in 3 dimensions, there is no like CFT for this. Just like, for example, if you look at this theory in 4 dimensions, right? This is known not to produce any CFT. Has any of you looked at the Wilson-Kogut review? I highly recommend it. I mean, it was written in the heyday of this stuff, and you get really inspired. First of all, some of these results are already in there. And the review was, it was based on many lectures that Wilson gave at Princeton University. I believe it was in the year 1973 or 4, something like that. Yeah, he was visiting the institute, and apparently David Gross told him, "You can give as many lectures as you want, And then he gave something like 17 lectures in a row. And Kogat was a postdoc at the time, and he took very good notes, and then together they turned it. It's a truly historic document, which if you really want to learn about how RG was born and how RG approached to critical phenomena, it's a great place to look at. And one of the things that they really agonize about is there a fixed point in 4 dimensions? Like they try to really squeeze out some kind of fixed point behavior out of this, and they couldn't. I mean, basically this series is just infrared-free in 4 dimensions, whichever way you slice it. And the only fixed point that we do know about is this so-called Caswell-Banks-Zaks fixed point, which, wow, that's yet another large N limit. That's called the Veneziano limit. But I'll stay away from that for the moment. There you just basically add NF species of quarks, and then you take the limit where both n is sent to infinity, the number of colors, and NF is sent to infinity. And if you just fine-tune the ratio, then you can end up in the fabled conformal window, which actually was a amazing paper by Bill Caswell in 1974, and he was a student of Kurt Collins, and he computed the 2-loop beta function. And then he realized that when you add 16 flavors of quarks, when the theory is barely asymptotically free, the 2-loop contribution is positive, and you get a weakly, very, very weakly coupled fixed point. And that has been confirmed by lattice results. Tom DeGrand, actually, I highly recommend. He wrote a review of modern physics about the search for conformal windows, so it's a great resource. So all these conformal, so yeah, I should add, I'm not sure if I should call it an exotic or generic. I think it's somewhere in between, but right, yeah, I tend to call them Caswell-Banks-Zaks. Yeah. So there are also these. So if you really want to be in D equal 4, CFT without SUSY, without supersymmetry, the only known possibility known is the so-called Caswell-Banks-Zaks. And they consist of like SUN gauge theory, SUN with NF quarks, massless quarks, in the Veneziano limit. Veneziano limit. And the Veneziano limit is basically NF going to infinity, NF, both N and NF sent to infinity, and this ratio X, which is NF over NC, specially chosen. You have to choose it very, very specially. Specially chosen. So without this kind of gymnastics, it's extremely hard to get conformal behavior in even dimensions. Because usually beta functions are positive and there is nothing to defeat them and stuff like that. But maybe. Yeah, I should also mention, since all of you have read Peskin and Schroeder, and Dan specifically wanted me to talk about Epsilon expansion. So for example, if you
just to let you know, Igor, we're about 3 minutes now.
Okay. So let me just finish in. Yeah, essentially, the thing I wanted to say is the following: that in addition to large N expansion, these type of models also have something called the Wilson-Fisher epsilon expansion. Wilson-Fisher 4 minus epsilon expansion. And essentially, it's based on the following fact that that if you compute the beta function for this coupling, it has the term minus epsilon lambda in addition to the positive term, which is n plus 8 lambda squared divided by 8 pi squared. And then there are some higher order corrections. And then you see that for any n, so if you look at this, you see that there is an IR fixed point. So there is an IR fixed point. So this actually ties to your question very much, because while in 3 dimensions lambda looks like it just goes to infinity, in 4 minus epsilon this flow is very short. Like you still have the UV fixed. So this is the picture in 4 minus epsilon. There is UV CFT, and here the IR CFT is very weakly coupled. It just sits at the coupling. So when you solve this equal to 0, you find that lambda star is only epsilon, so it's 8 pi squared divided by n plus 8, plus some higher order corrections. So you see that it's actually suppressed both by the small epsilon and by the large n. And this formula is in Peskin and Schroeder, so I don't need to give another reference. But you learn one important thing, that when you take the large n limit of these vectorial theories, you also need to do something similar to the 't Hooft limit. Namely, you have to take lambda to be of order 1 over n. So this large n limit, so the vectorial large n limit, large n, is where lambda is taken to be of order 1 over n. And it's similar to 't Hooft, who took G Yang-Mills squared to be of order 1 over n. And then just the one final thought as an appetizer, since I didn't get to start about tensor models, is, for example, if you take a model of the rank 3 tensor phi ABC and write down a particularly chosen interaction of the form, let me just write it down, G phi A1 B1 C1 phi A1 B2 C2 phi A1 A2 B1 C2 phi A2 B2 C1. Then something amazing. So you just take this special index contraction. You find that there is a large n limit where G has to be taken to go like n to the minus 3 halves. And then a very small type of diagrams dominates called Mellon diagrams. Then so-called, so the simplest Mellon diagram is like this. Yeah, so Mellons dominate. In this limit. Well, it turns out that in this limit, the dominant, say, propagator correction is the so-called snail. So here, in this vectorial large n limit, you just have snail dominance. So here is basically, in a nutshell, the story. It's like a battle of snails and melons. In the vectorial limit, snails win. Then for matrices, it's a draw, kind of. They both are important. And then in this limit, amazingly enough, snails lose and melons win.